Hello, friends. Welcome to yet another video of YouTube channel Tech Guru Gautam Prasad, and let me welcome you to this new video, which will deal with the some of the basic laws that rules the world of electrical engineering, and this is very important to properly understand those laws. And let me talk first about the Ohm's law in this video. So Ohm's law states that at the constant temperature, the current through an ideal resistor is directly proportional to the voltage applied across the resistors. So this is very simple. If you take a resistor, apply certain voltage DC or AC, this is going to be uh, I is directly proportional to V or V is directly proportional to I. So both are correct as far as uh, the electrical circuit is concerned. And the proportionality constant in the case of I directly proportional to V or V directly proportional to I is R. So, uh, this proportionality constant V equal to IR or RI, the shields here, as you can see, V equal to RI. Ohm's law deals with the relationship between voltage, current, and resistance. So this can be shown as I equal to V upon R. If you interchange these values, you will get this. And V equal to IR or I equal to V upon R. And this is basic. In the circuit analysis of small electrical circuits, basically this is very much applicable. And here is the photograph of George Simon Ohm, German scientist who proposed Ohm's law in 1827. So, he is the great scientist who established the relationship between V, I, and R. Now, we had used a terminology called ideal resistance. You might be thinking, what is an ideal resistance? So, this ideal resistance is that resistance which possesses the property of pure resistance, and also it doesn't change resistivity due to the change in voltage or the uh, current passing through it or voltage applied on it. This is called Ohm's law triangle, and you have been shown here the relationship VIR. So, if you take V is equal to IR, if you take I, then it is equal to V upon R, and if you take R, it is equal to V. So, this basically, V upon I. This basically lets you remember the relationship sometimes. Those who are beginners confused in these relationships, so for them it is the best way to bear it in the mind, right? So determining the power now in the Ohm's law. So power, as you know, is the multiplication of voltage and the current. Here also it is the product of V and I. So P is equal to V and I, that is product of voltage and the current in the circuit, and it can be shown in various ways. P equal to, if you substitute this V equal to Ri as we had seen earlier, then it becomes I square R. So P in the circuit is also equal to I square R. If you want to change it in terms of voltage, then substitute this value I equal to V upon R here. So P becomes V into V upon R. That means V square by R. So in all these three terms, you're going to P equal to V into I, R equal to V square upon P, R equal to P square, P upon I square. So using this formula, you can calculate the value of the resistance having given the voltage and the power dissipated in the resistance. So these relationships are very useful in doing the calculation, and particularly those who are beginners in the field of electrical engineering, they have to solve these small problems, and for them these relationships are quite useful. Again, here as you can see, P is equal to V square upon R. So R becomes V square by P, and becomes square root of PR. So again, P is equal to I square R. If you use this relationship, R is equal to P upon I square, and I becomes a square root of P by R. So V equal to square root of P R, and I is equal to the square root of P by R. So if you want to bear in mind, this is quite useful relationship. Why now question arises, why temperature is kept constant in Ohm's law? This has got a very simple um, reason. Because with the temperature, the resistance that you are using in the case of Ohm's law, Ohm's relationship, this varies. This varies. So that is why it is advised to keep the temperature constant. Otherwise, this your circuit is not going to follow Ohm's law. Now the question arises, what are the usage of Ohm's law? There are thousands of applications of Ohm's law in the daily life. We will show here a few of them, but there are thousands. The conventional domestic fan regulator, you must have seen the conventional one, not the regulator nowadays being used, because there is a difference in their working. So the earlier, basically a resistance, variable resistance was being put in the fan circuit, and the changing of the resistance was causing the current through the fan change, and that was regulating the speed of the fan. So here it was resistance, variable resistance being used. In the potential divider circuit or the voltage divider circuit, this law is followed. So divide, uh, this is used to divide the source uh, voltage across the output resistance. So this is a technique by which you can, increase or decrease the voltage level for a particular load. In the electronic circuits, there are many purposes where the intentional voltage drop is required to supply a specific uh, voltage across the different electronic elements. And this is done using Ohm's law by putting resistance of a particular value in the circuit. In mainly DC ammeter or DC measuring instrument, the shunt is a uh, kind of resistance, a small resistance that is used to divert the current so that it protects the measuring instrument, because many of the measuring instruments are not able to handle a high value of currents. So it is required to only measurable quantity of the current is passed through the instrument, and rest of the high value of the current is diverted from the instrument, and it keeps the instrument safe, and the rest of the current is diverted using the shunt resistance. Shunt is a very small value of resistance, as I told you earlier. Here also Ohm's law is used, and this list continues in numerous examples of Ohm's law applications. Now comes the limitations of the Ohm's law. The limitations of the Ohm's law are outlined here. This law cannot be applied to the unilateral network. Now, what is unilateral network? Let us understand. A unilateral network has unilateral elements like diode, transistor, etc., which do not have the same voltage current relationship for both directions of the current. Like diode lets the current pass in one direction, and it you know, stops the current from the other side. So its behavior in two directions are not the same. So here, Ohm's law fails to obey. Ohm's law is also, so the second point says, Ohm's law is also not applicable for nonlinear elements. Nonlinear elements are those which do not have current exactly proportional to the applied voltage, and that means resistance value of these elements for the different values of the voltage and current. So the linear relationship uh, obeys, whereas the non-linear relationship of V and I does not obey the Ohm's law. So examples of non-linear elements are diodes, transistors, thermistors, light-dependent resistors, incandescent light bulb, vacuum tubes, Zener diode, and there are many other examples like semiconductors are also not obeying Ohm's law, like silicon, germanium. These are the materials which don't tend to obey the Ohm's law. So essentially, any component where the relationship between voltage and current is not a straight line, meaning the resistance changes depending on the applied voltage or the other factors like temperature or light intensity. So there you don't um, you know have the use of Ohm's law. So this is counted in the limitations of the Ohm's law. Now coming to the last part, that is the verification of Ohm's law. Now how to verify the Ohm's law? This is a experiment that our beginners have to do in the lab. And by verifying this Ohm's law, they get the confidence, this Ohm's law, that it is a small experiment is really works. So how to verify that? So aim is to verify the Ohm's law. Apparatus required is you require a resistor of 5 ohms, then you require a voltmeter for the of the range of 0 to 5 volts, an ammeter 0 to 2 ampere, and battery of 5 volts, a plug and rheostat. IR, V equal to IR, where V is the voltage, I is the current, and R is the resistance. Now, the circuit arrangement for this experiment is shown here. You have to connect the instruments in this fashion. Uh, Connect the circuit as shown in the picture. Consider that R is the resistor, ammeter, and DC voltmeter, battery, BT, rheostat, key in series. Connect the voltmeter parallel to, all these are connected in series, whereas the voltmeter has to be connected in parallel to the resistor. Like here it has been shown, this voltmeter has been connected across this resistor to measure the voltage, you know, voltage drop in this resistor. Okay. Now by using the rheostat to change, here is your rheostat that you are changing. So you have to adjust the voltage from 0 to 1 volt and note down the corresponding value of the current with the help of the ammeter. And you have to prepare a table like this. In the first column you have serial number, then you have potential difference V and current in the second column. Now after you know having these values noted down, you have to draw a graph between V and I. uh, I is plotted on the x-axis and V is plotted on the y-axis. Then if you join the lines, if you join the corresponding voltages of V and I, you will find it is almost a straight line. So that verifies the Ohm's law, and you get satisfied that Ohm's law is a actual law and it is not an imaginary law. So by doing this experiment in the laboratory, you can verify this law. Now, there is yet another law in the field of electrical engineering. This is also an important law, and that is related to the world of electromagnetic induction. So, the Faraday's law are two in numbers, the first law and the second law. We will go through one by one. So, what actually Faraday's law of electromagnetic induction states? The Faraday's law of electromagnetic induction, also referred to as Faraday's law, is basic law of electromagnetism that predicts how the magnetic field will interact with the electric circuit to produce an EMF or electromagnet electromotive force. This phenomena is also known as electromagnetic induction. With this picture, we have tried to show you there is a coil here. You can consider it to be a solenoid coil. So this is an insulating pipe, and there is a winding on that basically, and this is connected to an ammeter or a galvanometer, whatever. Okay, so and there is a piece of electromagnet, and this north side is towards the coil, and south side is away from the coil. So if you take this magnet, not electromagnet. If you take this magnet inside this solenoid, then you will find there is some deflection in this ammeter or galvanometer. Okay, when you keep it stationary after taking it inside the solenoid, there is no deflection. It comes to zero. And if you quickly bring it out, then also deflection takes place. But this time deflection takes place in opposite direction. So when you take out the electromagnet quickly out of this solenoid, then the deflection comes in opposite direction. If you take it inside the coil, the deflection comes in a particular direction, that is forward direction, you can say. But when you insert it inside the coil, it gives you deflection in opposite direction, reverse direction. So considering the galvanometer has got a zero position, and it can give you deflection in either side, both the sides. Okay. Now EMF induced in this coil is given by minus n d phi by dt. E is the electromotive force, n is the number of turns on the coil, and d phi by dt is the rate of change of magnetic flux with respect to time. So that's it. And Faraday's law states that EMF will be induced in the conductor when it is exposed to the changing magnetic field. This is the underline, bottom line of the electro Faraday's law of electromagnetic induction. Now coming to Lenz's law, what this Lenz's law of electromagnetic induction states. So this states that the direction of the induced current is caused only when you have a closed circuit in the induced EMF circuit. So the coil, has got EMF induced in it, but unless this circuit is closed, you are not. If you are connecting some kind of load in this circuit, then this circuit is closed, and then only the current will flow. That will be caused induced current because it is caused because of induced voltage. So this Lenz's law states that the direction of the induced current will be such that this induced current, will flow in such a manner that the magnetic field created by the induced current, it is talking that if the uh, induced current is causing some magnetic field uh, in the coil conductors, then this will induce in such a manner that it opposes the initial changing magnetic field. It starts changing the it starts opposing the magnetic field. So basically, in order to simplify it, I would like to state that here this coil, you know, sets a flux in such a manner that there is a magnet inside, and that has got north side. You can consider a magnet is there inside, created by uh, the current flowing into the coil. It is such that its north pole is on the right side and south pole is on the left side, and north faces the north. So you can think the north side of the uh, electromagnet produced here will oppose this north side. So when you are taking it inside, you will face some resistance because of the production of electromagnet due to these coils. And where from this electromagnet is produced? It is produced because of the EMF and the current caused in this circuit. So current is current, induced current is causing an electromagnet inside this coil. You can imagine to have a electromagnet which has got north pole on the right side and south pole on the left side. On the contrary, when you take it out, once you have inserted it and your this magnet is here inside the coil, and then if you keep it stationary, this magnet is stationary inside this coil, then there is no deflection in this ammeter or galvanometer. But when you quickly draw it out, quickly take it out, then also the deflection is there, and you will face a resistance once again when you are trying to take it out. Because when you are trying to take it out, the flux linkages with the conductors of this coil again induces EMF, and that EMF causes current, induced current, and this current again creates the electromagnet. Like, you know, on this side you have north. This time your current is causing electromagnet which has got south side on the right side and north side on the left side. The direction of the electromagnet this time has reversed. The south side on, contrary to the earlier statement I made, it was on north side was on the right side and south side was on the left side. Here it is just reverse. The south side now has appeared on the right side and north side has appeared on the left side. So this time south of the electromagnet is now facing the north of the electromagnet. So it is trying to attract. So when you are trying to take out this electromagnet out of this coil, then it is trying to attract. South will attract the north. So again, when you are trying to take it out, it will not take you out this magnet easily. So there will be a magnetic drag. This is called magnetic drag. So this electromagnet produced inside the coil again opposes the relative motion of this electromagnet. And this is the whole thing that, explains the Faraday's law mixed with, Lenz's law. Lenz's law states that the direction of the current is in the electromagnet is as such. In this coil, the direction of the current uh, is such that the electromagnet produced in this uh, coil, tends to oppose the relative motion of this magnet. Okay, so that is what Lenz's law says. And sometimes, we put a negative sign here just to signify the fact given by the Lenz's law. So Lenz's law, we can also say that defines the polarity of the induced EMF. This negative sign uh, has been placed in the honor of the Lenz's law. Okay, so this shows the polarity of the uh, current or the EMF. All right. Now, the direction of the current can also be determined using Faraday's right hand rule. Here, Faraday's right hand rule says if you stretch your fingers, forefinger, thumb, and middle finger, in such a manner that they are all perpendicular to each other, then if your if your magnetic field is shown by the forefinger, and the direction of motion is given by the direction of the thumb, then your direction of current is given by induced current. More precisely, the direction of the induced current is given by the direction of the middle finger. So, this Fleming's right hand rule gives you the direction of current in the conductor, having having exposed you have exposed the conductor in the magnetic field B, and you are trying to rotate the conductor in the direction of the thumb. All right. So In the case of electromagnetic induction, uh, you you predict the direction of the current using Fleming's right hand rule. Okay. Now, the Faraday's experiment that I was talking earlier has been explained in this picture. You have taken a galvanometer here. If you take the electromagnet inside and if you keep it stationary, then it becomes, stationary at zero, the galvanometer. If you take it out, again, it gives you deflection in other direction. Look into this galvanometer. It is giving you direction on the right side, and here when you are taking it out, it is giving you deflection here on the opposite side, that is left side. So that is how it is explained. Now let me proceed to the Faraday's first law. So the Faraday's first law states any change in the magnetic field of a coil wire will cause an EMF induced in the coil, and this EMF induced is called induced EMF. And if the conductor circuit is closed, the currents will also circulate through the circuit, and this current is called induced current. The method to change the magnetic field by moving the magnet towards or away from the coil, by moving the coil into or out of the magnetic field, by changing the area of a coil placed in the magnetic field, by rotating the coil relative to the magnet. Okay, and what the second law of Faraday's law of electromagnetic induction states? It states that the magnitude of the EMF, this talks about the magnitude, so you have to mind it. Uh, uh, the first law and the second law. Second law talks about the magnitude of the EMF in the coil. First law was, talking about the change in the magnetic field, the induced is called EMF. This is basically talking about the direction of the induced current, whereas this thing is talking about the magnitude of the. So they uh, talk to different things, and that you have to be alert about. You have to be careful about. So this it states that the magnitude of the EMF in the coil is equal to the rate of change of the flux linkages with the coil. The flux linkages of the coil is the product of the number of turns in the coil and the flux associated with the coil. So two things it is saying, N and d phi by dt. So it is the product of both N and d phi by dt as shown in this equation. And there is a negative sign, as I explained you, that because of Lenz's law, that the polarity is such that it opposes the very cause producing it. How to increase the EMF? Now, this is a small quantity of EMF that I have explained you. But if you want to produce a huge amount of EMF, just as you do in the case of alternators, then what needs to be done? Or in the case of transformers, so what has to be done? So basically, by increasing the number of turns uh, that you have to keep in the mind, this is a thing that increases the EMF. Okay, so by increasing the magnetic field also, B, that is called the field strength, magnetic flux density, you can increase this value. So the second way is to increase the magnetic field by increasing the speed, the relative motion between them, the relative motion of the conductor, or the relative motion of the magnet that you are rotating, that you are, inserting. In this case, you are inserting and taking it out. So if you speed up the relative motion, that will also lead to increase of the induced EMF. So there are three ways suggested here. Either you increase number of turns or you increase the flux density of the magnetic field or the strength of the magnetic field, or you speed up the uh, relative motion between them. That you, if you are doing all these three together, then also your EMF, the total of the EMF that you are producing will increase. Applications of the Faraday's law. Faraday's law is the most basic and important law of electromagnetism, and this law finds application in many of the machines, in industries and medical fields also. Power transformer uses Faraday's law. You have electrical generators, that uses electromagnetic Faraday's law of electromagnetic induction. Transformers use, mutual induction. The induction cooker is the fastest way of cooking, and it also works on the principle of mutual induction, because eddy current is generated in the uh, plates of the cooker, that acts as the secondary part of the transformer. Sometimes the primary happens inside the cooker. Okay, the electromagnetic flow meter measures the velocity of certain fluids. So fluid is uh, passed through the pipe, and being the conductive, uh, the fluid being conductive, passes through the magnetic field, and the EMF is induced. So when magnetic field is applied to the electrically insulated pipe, which conducting fluid are flowing, then according to the Faraday's law, electromotive force is induced in it, and then induced EMF is proportional to the velocity of the fluid. So that is how we measure the flow of the liquid, the amount of flow taking place through the pipe. So, from the basis of the electromagnetic theory, Faraday's idea of lines of force is used in well-known Maxwell's equations. According to Faraday's law, change in the magnetic field gives rise to the change in the and electric field, and the converse of this is the Maxwell's equation. It is also used in the musical instruments like electric guitar, electric violin, etc. Okay, now coming to the Lenz's law. I hope I have explained it in the earlier case, so I'm not explaining it. The same thing has been repeated here, so I am proceeding. Uh, Fleming's left hand rule. This I have not explained. So this is a picture of Fleming, and this is the left hand rule. So basically, it is same as the right hand rule that I had explained you. Here also, this left hand rule basically uh, is used to uh, the define the direction of motion of the conductor if placed in a magnetic field. So if you place a current carrying conductor in the magnetic field, it experiences forces, and its direction of motion, its direction of force, uh, is given by left hand rule. So if you stretch your fingers in such a manner that your thumb, forefinger, and middle finger are stretched perpendicular to each other, and your direction of current is given by the middle finger, magnetic field direction is given by the forefinger, then the direction of motion is perpendicular to both of them, and it is given by the thumb. So that is what this Fleming's left hand rule says. Right hand rule gives you the direction of the induced current. Left hand rule gives you the direction of the motion. That is the difference between left hand rule and right hand rule. Fleming's left hand rule and Fleming's right hand rule. So having explained all this, I end this video here, and thank you very, very much for being with me and staying with me throughout the video, and hope you have enjoyed learning uh, all these fundamental things. fundamental laws that rules the world of electrical engineering. And keep enjoying my other videos and stay tuned with me. Uh, don't forget to like, subscribe, and comment. Your comments are especially very useful to me, which gives me insight how to make my videos better, how to make it more useful for you all. So thank you very much.